This video is on reaction rates. Up to this point, we talked about factors that affect the rate of a reaction, but now we're actually going to look at the actual rate. So what is a rate? Well, it's the change in concentration of a reactant or a product per unit time. So here we've got a reaction. A is our reactant, yields B. Well, when we put A in square brackets, that means the concentration of A in molarity, or moles per liter. Remember, that's a capital M. If we put a delta sign outside of that A in brackets, that delta means the change in the concentration of A. And in chemistry, that delta sign, or in all science classes, means the change from final minus initial. And so delta A would be the concentration of A at the final time minus the concentration of A at the initial time. So time is a little t, and it can have different units. I see seconds a lot, you can see minutes, hours, but it can really be any unit of time. So delta T, and again, this is a lowercase t, capital T is reserved for temperature, but the delta T would be the change in time, so it would be the final time minus the initial time. All right, so let's think about units. Well, a rate, they're always positive. It's kind of like your speed in a car. You know, how fast are you going in miles per hour? Well, how fast is your reaction going in molars per second? And so you can see like a capital M over seconds. Again, the time unit could be something different. Or you'll see molars seconds to the -1, which means the same thing, molars per second. Now, A in this reaction is disappearing. Our reactant is disappearing, and B, our product, is appearing. Now, it only makes sense if a rate is positive. So the average rate of disappearance of A is equal to negative delta A divided by delta T. Because remember, A's concentration is going down because it's disappearing, and so that final concentration is going to be smaller. So like the smaller number minus the initial concentration is going to give you a negative number. So that's why we put that negative sign out front. Okay, the rate of appearance of B is just delta B over delta T. Okay, so again, rate is the change in concentration per unit time. Okay, so let's look at a real reaction. Here we've got a decomposition reaction. We've got nitrogen dioxide gas decomposing into nitrogen monoxide and oxygen. As time goes by, the concentration of nitrogen dioxide will be decreasing. And so our reactant concentration will be decreasing. I'm just going to draw an arrow down here. And the nitrogen monoxide, a product, it's going to start making these products, so its concentration will be going up, and the oxygen concentration will be going up. So we could write these rate expressions like the rate, let's go ahead, is equal to the disappearance of the concentration of nitrogen dioxide per unit time. Or we could have written the rate is equal to the appearance, so no negative sign, of the nitrogen monoxide per unit time. Or we could have written that it was the rate of appearance of our other product, which is oxygen, per unit time. So again, rates are the change in concentration per unit time. Well, here is a data table of actual concentrations of nitrogen dioxide over time and the products, nitrogen monoxide and oxygen. So as you can see here, the nitrogen dioxide, which was decomposing, at time 0, we had 0.01 molar. But after 50 seconds, that concentration went down to 0.009. After 100 seconds, it was 0.0065 and so forth. And it went all the way to 400 seconds and it had decreased down to 0.0031. Now the initial concentrations of the nitrogen monoxide and oxygen were 0. So at time 0, or our initial time, the concentration of nitrogen monoxide, we didn't have any product. And then as time goes by, you can see the concentrations increase for these products. So we can calculate, using data like this, we can calculate what we call an average rate, but we can do it during some time frame of the reaction. So how would we calculate the rate of the change in concentration of nitrogen dioxide during the first 50 seconds of the reaction? Okay, so again, the rate is going to equal the disappearance, so the rate of the change in concentration of nitrogen dioxide per unit time. Okay, now that final concentration, so the concentration at 50 seconds is 0.0079. So the final concentration minus the initial concentration, which is 0.01 molar, over our delta T, which our final time was 50 seconds, and our initial time was 0 seconds. Okay, when we do this math, so 0.0079, so this, we need a negative sign out here, the rate of disappearance, we're going to get a rate of 4.2 times 10 to the negative fifth molars per second. Okay, so that is what we call the average rate during the first 50 seconds of the reaction. All right, here you can see a table. And so during the first 50 seconds of the reaction, our rate was 4.2 times 10 to the negative fifth molars per second. Okay. So what I would like you guys to do, so you can pause the video and go ahead, look back at the data and calculate the average rate during this time frame, 50 to 100 seconds, calculate the average rate here from 100 to 150 and so forth. So finish completing this chart. So you're going to calculate 4 rates. When you're done doing the calculations, go ahead and resume the video. All right, what did you notice about your average rates as time went by? Well, here's a graphical display of that data for that decomposition reaction. So on our y-axis, we have the concentration in moles per liter, and down here, this would be time. It looks like my axis got cut off, and that would be in seconds. Okay, so notice what happens. This green line here is the concentration of nitrogen dioxide, and yes, it's going down over time, and the nitrogen monoxide is going up and the oxygen is going up. But notice the slope of this line. The slope is the concentration over time, the y over the x. Notice that the slope of the line is not constant. If it were constant, it would be a straight line. As a matter of fact, the slope of this line is going down as time goes by. Did your data show that the rate of the reaction went down over time? How about the rate of formation? Here, we're forming the nitrogen monoxide. The slope is really steep. It has a large slope. And then over time, that slope the rate is going to go down. The slope of that line is getting smaller. So your data should have shown that your the rates of these reactions as time goes by would be decreasing. So now let's think about why that would be. Why would your rate change with time? And I'll give you a start to your thought process. And then I want you to think about it some more and write down some notes. Your rates are going to decrease as your reaction proceeds. This is because, well, the concentration of your reactants is decreasing. So think about that. Maybe think about the collision theory and write down some ideas. Why is this happening? Why are these rates decreasing as our concentration is decreasing? Okay, now, what if we wanted to know the rate at one particular time? Because you know the rate is changing over time. What if we wanted to know exactly the rate of a reaction at a certain time? Well, that's called an instantaneous rate. We have to do a little work to get that. So what we have to do is we have to draw a line tangent to the time of interest. We'll calculate the slope of that line that we've drawn tangent to our point of interest. Now the slope of that line will be the rate. It will have the units molars per second. So here is this graph again, and we're looking at instantaneous rates. And I am not sure of, I've cut this axis off, but I'm not sure of the time here. It looks like it's probably, oh, I don't know what it is. But anyway, at this time here, let's say we wanted to know the rate at this exact time. We would draw a line tangent to that point, and then we would get the slope of that line. So it's the delta y, the change in y over the delta t, and so it would be 0.0026 divided by 110. That will give you the rate at that exact time. And over here, let's say that we wanted to know the rate right at this point in time. Draw a line tangent, get the slope of that line. So if you need to review slope, I'm sure there's a Khan Academy video on slope, but it's always the change in y over the change in x. If you want the instantaneous rate, what you do is you draw a line tangent to the point in time of interest. All right, our next video will talk about reaction rates and the stoichiometry of the reaction. Have a good night.